Okay, so as promised, here comes some optimization review. So optimization. Now, I'm not going to list out the cookbook recipe of how to do this. You guys have that note, or you can find it on Classroom from a while ago. I'm just going to hit a couple more examples to kind of refresh and revisit stuff. So optimization means at its most basic, making something as good as it can get, making it the best it can be. So optimization can be making something as large as it can be. So if you're making, you had a given amount of fencing and you wanted to enclose the largest area, sometimes optimization is maximizing. Sometimes optimization is minimizing. If you wanted to figure out what the least cost to do something was, that would optimize it as well. So optimization is making the best, sometimes biggest, sometimes smallest. So let's look at a couple of examples of how we can do some optimization. So an easy one would be a cost based on an object. So imagine we had the following scenario. We want to create I don't know, how about Jad has to store his My Little Ponies. So Jad is going to store his My Little Ponies in a display box. Okay, so it's going to be a rectangular box that he's going to store his My Little Ponies in because Jad has like a banging collection of My Little Ponies. So here we go. So here is the box that Jad stores his My Little Ponies in. Now, Jad is very particular about his aesthetics, and he knows that the width of his box has to be double the length of his box. So if this is going to be L, this is going to be 2L. And then the height is, well, it's just the height. Now, optimization problems can come in many different ways. I could give you a fixed cost and say, build the largest box that you can here. Or I could give you a fixed volume and say, build it for the smallest amount of money that you can. So I'm going to tell you that the top of the box is glass because Jad likes to be able to look in at his My Little Ponies and see them. And so glass is expensive. Glass is going to cost, I don't know, how about we make it 75 cents per centimeter squared. The sides are going to be curly maple, and Jad is down with the curly maple. Curly maple costs 25 cents per centimeter squared, and that's all of the sides. So that is this side and the back as well. And then the base, Jad doesn't care so much about the base. It's just going to be made from a little bit of laminated wood, and it only costs 10 cents per centimeter squared. So Jad's collection, it's pretty significant. So Jad has figured that the least volume that he can get by with is going to be the volume it has to hold a total of, I don't know, 20 liters of volume. Now, volume can be measured in cubic centimeters, cubic meters, or liters. And I'm going to tell you, so then the question would be what dimensions minimize the cost to build this? Okay, so what we need to do is we need to start working on this. Well, first thing we're going to need to do is this is in centimeters and this is in liters. And we should know by this juncture that 1 liter is equal to 1,000 cubic centimeters. Okay, now, by all means, you should be pausing this and giving this a whirl if you're trying to practice, but otherwise, watch along. So I know that I need the dimensions. So I'm given different things. So what am I trying to optimize? I want to minimize the cost. So it's really, really important to say that's what we want to minimize. So I know I'm going to need to have a cost expression that is what it is that I'm going to differentiate because I have to differentiate the expression that I am optimizing. So there's some other things that we know. Well, we're going to need the volume calculation. So we know that volume of a rectangular prism is length times width times height. But in this case, the width is 2L and then L and H. So if I simplify that, it's going to be 2HL squared is what the volume is. But I know what the volume is. The volume is actually 20,000 cubic centimeters. Okay, so there's my volume. It's 20,000 cubic centimeters. Now, I'm going to come back over here. I know we're going to have to do some more work here, and you probably have some suspicions, but I'm going to kind of do this more linearly. So I'm not going to jump to cost right away. I'm going to start with surface area. Okay, so surface area, and I'm going to identify, like I could come up with an expression for the whole surface area right off the bat, but I want to identify the sides that are all of like cost. And so I'm going to just label them off. I'm going to say, all right, well, the top has a certain cost. Well, the top is going to be 2L times L. So the top is 2L squared. And then I'm going to say what the bottom is. Well, the bottom has the same dimensions as the top, so it's also 2L squared. And then we have the sides. Now, I'm going to have 2 of each of these sides. So one side is 2L by H, so 2LH, and then the other side is just LH, LH. And these are all the sides. So I'm going to simplify this a little bit. So we're going to have 2L squared plus 2L squared. You might say, well, can't you make that 4L squared? Yeah, I could, but that would defeat the purpose because those sides are going to cost differently. So I don't want to do that yet. Now, these are all the same cost, so I can simplify this. So 2LH plus LH is 3LH times 2 is 6LH. So there's my expression for surface area. Not as simplified as it can get, but it's simplified for our purposes. Now I'm going to add the costs in here because that's what we're really after. So we have that the cost is going to be equal to, well, the top is 75 cents per centimeter squared. Now you could do it as 0.75 and do it in dollars, or you could do it as as 75 to do it as cents. I think I'm going to do it as 0.75. So I'm going to say 0.75 times 2L squared. Squared goes there. And then the bottom, similarly, well, the bottom is going to be just 0.1 times 2L squared, plus the sides are 0.25 times 6LH. Go ahead and do some simplification. So that is going to be 1.5L squared plus, I'll do it in excruciating detail, 0.2L squared plus, what is that? I guess it's $1.50, so $1.5 or 1.5 LH. Okay, simplify a little bit more. And so we say that's going to be, I guess that's 1.7 L squared plus 1.5 LH. And that's what cost is equal to. Now, given that we've already done the implicit differentiation unit, we could actually differentiate this right away. But what are we going to differentiate it with respect to? Well, this is a weird one because it's not with respect to time. It's with respect to the variable. So when it comes to optimization, we really want to get it in terms of one variable. And that's where this is going to come back in. So I can rearrange and I can solve for H here. I mean, in theory, I could solve for L, but why would I do that? We have a linear H here, a linear H here. So the substitution is going to be really easy. So I'm going to divide both sides by 2L squared, divide by 2L squared, and we're going to get that H is equal to, I guess, 10,000 over L squared, or L to the negative 2. So I'm going to come back here and say that's lovely. I can substitute that in. So we have 1.7 L squared plus 1.5 L times that H value, which is going to be 10,000. Actually, I might write it as the ratio here, over L squared. And I can simplify it again. So we come along here and we can say, all right, this is going to be 1.7 L squared plus 1.5 times 10,000 is 15,000. That L is going to go with that L, so it's over L, so L to the negative 1. And that is what the cost is equal to. So now we have what we're trying to optimize in terms of just one variable. So now I can differentiate. So in theory, it's dcost by dl or cost prime. I'm going to do dcost by dl, and that's going to equal 3.4L. And I don't need a dl by something because it's with respect to L, minus 15,000 over L squared times, well, I was going to say dl by dt, but it's not really. So that's it. Okay. So now we can say I'm going to let the cost by dl equal 0 to find max mins or criticals or optimize, whatever. We're going to set that equal to 0 and solve. So I'm going to pop that over. So we're going to get then 15,000 over L squared is equal to 3.4L cross multiply. So we're going to get 15,000 divided by 3.4 is equal to L cubed. And then we're going to cube root both sides. So cube root this side, cube root this side. And we're going to find out that L is equal to whatever the cube root of this is. I guess I should probably calculate that. Let me grab a calculator. Here we go. Come on up. Come on back. All right, so we've got a calculator here, or we had it here, turn it on. And so we're going to do the third root. So I can go math third root of 15,000 divided by 3.4. So we found that the length is 16.40. So we've got 16.40. That's what the length is. And so then the width is double that. So the width would be equal to, I guess, 32.80-ish. And then the height is going to be equal to, well, I'm not going to bother with the calculations. You know how to do that. You're going to take the height and you're going to solve it right here because we have what the length is. You can substitute it in and get your height. So there is an example of optimization involving some costs, right? So let's try another one. How about let's do a revenue problem. Okay, so revenue. What we have is Bree is going to sell cheese. Yeah, Brie, cheese, get it? She charges currently, I don't know, $15 per wheel of Brie. It doesn't need to be capitalized because we're talking about the cheese there now, of Brie. So every time she increases the price by $2, she sells 50 fewer wheels of cheese. Currently, she sells 400 per week. What price should she charge to maximize revenue? And then the second part of this question, she pays $5 per wheel. What price to maximize profit? Okay, so those are the two classic questions that we would ask for revenue and for profit. So we're going to need to make a revenue equation. So revenue, we know, is equal to the number sold times the price per. Okay, and so I'm going to set that up. And right now she is selling 400 per week. So she's selling 400 per week. And the price that she's selling them at currently is $15. And then we know that if she increases the price by $2, so I'm going to come back here and say if she increases the price by $2, she sells 50 fewer wheels of Brie. And she can do that multiple times. So I'm going to let an X go in here. So I would say let X rep the number of increases in price. Okay, and so then we would expand that, we would differentiate it, we'd set it equal to 0, and we would solve, and that's what it would tell us. And I don't think I really need to do that because these are some big numbers, and I'm kind of running out of space here. So that's what we would do for revenue. Now, when we consider profit, okay, so profit, what profit is, it's equal to revenue minus cost. So in this case, we have an expression for revenue. It's this big expression right here. So I can come along and say, well, it's, and you would already have this simplified by this juncture, but I'll just rewrite it. Minus 50x times 15 plus 2x. So there's my revenue minus cost. Well, she pays $5 per wheel. But it's not just once. She has to do that for however many she sold. That's why it's nice to label it like this. This is the number that she's going to sell. So it's going to be 400 minus 50x. Again, you'd expand all this, you'd simplify, you'd differentiate, set equal to 0, and you would solve. And there you go, Bob's your uncle. That would be an optimization problem that is done. Okay, so that is an example of a profit problem. Final one, and we're just going to kind of outline it. We're not going to fully work it out. And that is the one, different ones. It can be the one where you're swimming across a river at one rate and you can walk on land at another rate. That's the same thing as if you're laying a cable through an expensive area and a less expensive area, and it's trying to figure out what the best thing to do is. So imagine that we had the following. So we've got this river. Here we go. And here we go. And we need to get a cable from point A to point B. Now, the distance from point A to point B, the total distance is, let's make it, I don't know, 800 meters. So this distance is 800 meters. The river is 200 meters across. Cable laid in the river. So cable in the river costs, I don't know, how about $20 per meter, which is way low. And then cable on land, well, it costs, it's less expensive. It's $15 per meter. So the question is, and there's lots of questions that can be phrased about this one. We know that somewhere up here is going to be the optimal. It could be there, it could be here, it could be here. Probably not here, but who knows? What we need to do is we need to figure out this unique point, and then the questions can be asked differently. It could be, how far along land is the cable run on the other side of the river, or it could be, how far downriver from perpendicular do we aim for the cable that's in the river. So you just look at the context of the problem. Now, we know that this side is 200. It's labeled right there. And what we have here is a right triangle. So because we've got this right triangle, this is the hypotenuse of a right triangle. Now, there's two different places we could add a unknown dimension. We could say that this is x and this is 800 minus x, or we could say that this is x and this is 800 minus x. In theory, if you have great tenacity and perseverance, it'll work either way, but you really want to make your single variable be as part of this, because of course, what we're going to do is we're going to have to square that to get this expression right here. And then this piece can be 800 minus x. So we want to minimize the cost. So to minimize, if it's cost, that means we're going to need an expression for cost. So first thing I want to do is I want to find an expression for the distance of this hypotenuse. Well, Pythagorean theorem says that a squared plus b squared equals c squared. So c, this piece right here, is going to be equal to the root of x squared plus 200 squared. Okay, so that's going to be equal to the root of x squared plus 40,000. I think 1, 2, 1, 2. Yep, that's it. So there's the expression for this chunk right here. And then this chunk is just 800 minus x. So that's the length in meters. That's the length in meters. But we're not trying to optimize length. We're trying to optimize cost. So now I need to do cost is equal to, well, this chunk is going to be $20 per meters. So it's going to be 20 times this radical of x squared plus 40,000. And this chunk is going to be, well, it's only $15 per meter. So plus 15 times 800 minus x. And there's the setup. What we would do now is we would expand and simplify as much as we could, differentiate, set equal to 0, and solve for x. Okay, and then the x is going to be this distance right here. And you would need to answer the question as it was posed. It could be simply, what is the minimum cost? And then you would take that x value and you'd put it back in here and you'd figure out what the cost is. It might simply be, well, this is the distance downriver we need to aim, or it might be 800 minus x. So those are the main variants of optimization problems. So there you go. All good. Have a lovely day, children.